Okay, well, thank you all for joining us today on our discussion on how to be successful with dye sublimation printing. If you have any questions, please feel free to use the chat box, and myself, Natalie, and Andre will answer questions as we come in, as we go through, or at the end, depending upon how lengthy the question is. So I'm going to let Andre do a little introduction about himself, and then we'll get started.
Okay, hello everybody. Yeah, welcome to the Ultraflex Virtual Trade Show. Today our topic is color management in dye sublimation. My name is Andre Schwarz. I'm in this industry for, I don't know, a long time. Color management is something like my DNA. Yeah, I'm a very technical person, so I played a lot with printers, a lot of different medias, and I specialized myself in dye sublimation or textile printing in general. Before we start, I want to do some color management basics. This is kind of the foundation we need for the next steps. So maybe some of you heard some of these topics, but I think yeah, it's not bad to at least refresh some of the knowledge and stuff like that. So first step, what is color? And when you look for color in the internet, you will find, for example, at Wikipedia, that it's the characteristic of visual perception. So one aspect of appearance, a stimulus based on visual response to light consisting of the 3 dimensions of hue, saturation, and lightness. So what that means, we will see in the next slides. So one important fact is that objects don't have a color, so they have a surface, and light hits the surface and got reflected, and then some parts of the light got absorbed and other got reflected, and that's what we see as color. So because other beings out there, for example, birds, they have different eyes, they have a different eye architecture, so they see different colors, they see different things out of the reflection. When light hits the surface and all the light gets reflected, we perceive it as white. If all the light gets absorbed, we see it as black. And then you see it in the slide, 3 important radiations is 400 nanometers is blue, 500 is green, and 600 is red. And all the other are something in between. We'll see that later on in the slide. This is a typical German sentence, at night all cats are gray. But actually that's the true, because to see color, you need a minimum amount of light. Otherwise, everything you see will appear gray. So color is connected to light and the amount of light you see. Another very important fact is that we don't see with our eyes, we see with our brain. Our eyes are just the detectors to get the information. Then there is the nerve that gets this information to our brain, and in the brain we see. So that's where the picture got generated. This is the visual spectrum the human eye is able to see. So it starts at around 400 nanometers and it stops at 700 nanometers. That's the part of the wavelengths our eye is sensible for. Oh, that's the wrong direction. Another very important thing when we talk about this all color management stuff is that, as I said, we see with our brains, and our brains have learned how objects should look like. And for example, white. When you look at something and it's a whitish surface, then it looks white for us, even if it's a grayish light, like a white, like on a newspaper or something. Our eyes adjust to the lightest point in what they see, and then they adjust this as white. So what is white? This is a difficult discussion, huh? Because our eyes, our brain looks. I have a nice example. We all have seen that before when an old truck, whatever, passes you on the street, and there is a print on the truck with, for example, tomatoes. And due to the UV light, this is an old print. All the red pigments, they disappeared. So the tomatoes, they are not red anymore. They are yellow. But still, when this past trucks us, we see there are tomatoes. Because our eye, because we see with our brain, and in some parts the color is not even important to get the information. The most important part, color is perception. Color is nothing absolute. It is something relative, and everybody sees color different. Color is perception, like a temperature, like hot and cold. When I'm sitting in the living room with my wife, and it's and I'm in a comfort temperature. She's freezing, or the other way around. So yeah, the decent temperature is nice for me, and might be too cold or too hot for someone else. And it's the same with color. Color is perception. And another thing is that a lot of things have an impact on how we see color. So the gender, the age, your health condition, physical factors, and all this stuff has an impact on how you see color. This is an example of, yeah, we have four different reds, 4 different greens, 4 different blues, and 4 different grays. And this is an example how a red should look to you, and how it might look to someone else. But we agree this is all red, and this is all green, and this is all blue, and this is all gray. And this is one part why it is very, sometimes frustrating and actually difficult, or nearly impossible to discuss about color, because color is nothing absolute. If you like a color, or you think this is the correct color, then yeah, this is your perception, but it might be wrong. So a lot of things have an impact in how we see color. Another impact on how we see color is the light source, or the light conditions under we see a color. So, because as I said in the beginning, color, or seeing color, is the reflection of light. So the light, or the reflection of a different light source, will cause a different color. And this is what this sample shows. So these are different light temperatures. So normal light, daylight, is at around 5,500 Kelvin. Inside light is something like 3,000. And if you go to, for example, an exhibition hall or an event center, they have very bluish light sources. I have a nice example for that. Short story was a trade show in Germany, a big car trade show, and Mercedes wanted to show their new model. And the idea was to present the car hidden under a curtain on a stage. And then when they lift the curtain, the plan was that the banner inflated over the car and showed the exact same car. So a print shop, they produced it. It looks nice in the production place, and they installed it in this exhibition hall, and the car should be silver metallic, and in the hall it was green metallic. So Mercedes said, yeah, we don't accept that, we want to have a silver metallic car there. So they called, and I exactly knew what's wrong. So we measured the light temperature in this hall, and it was something like 9,000 Kelvin. So we adjusted the color management settings of their color management system, and then they printed it again with a light temperature of 9,000 Kelvin. Then they called me and said, hey, Andre, the prints, they look shitty. This will never, ever work. And I said, yeah, trust color management. And then they installed it in the hole, and it was silver metallic. So that was just the impact of the light conditions in the hole, screwed the colors completely. So this is also a very important fact. You see it here, this is a red car, and then 4 different light sources, and it's actually, yeah, like 4 different cars, but it's the same car, it's the same color, it's just different light conditions under you watch the car. Now a little bit more to our industry. So, for example, we have optical brightness on a lot of our materials, and this is what optical lightness do to materials when you just change the UV amount in a light source. So this is another impact. So there are a lot of things that have an impact on how we see color. This is a picture I like a lot to show, how our brain actually works. So you see felt A and felt B, and we all agree the colors are different, and they're not. If you just mark the A, I did that in Photoshop, and then I just moved the part on the B part, and you agree it is the exact same color. What happens there is our brain tricks us, because the brain sees this shadow, this cube shows, and wants to see in this shadow, and that's the reason it appears different to us, but it's totally the same. Stuff like this. So on the upper left you see dots, and there is nothing. On the upper right the lines are straight, and they don't look straight, and stuff like that. So this is all stuff that is happen in our brain. We skip this. This is not that important for now. And now we talk about color management. So we need to have something to communicate color, to discuss color, and to have something, kind of absolute color values. And color management allows us to have absolute values, because what is an absolute value? A wavelength is an absolute value. So a wavelength is a color, and even if everybody else might see this wavelength difference, this is an absolute value. So this is something we can use. And as computers, they work with bits and bytes, as we all know. Then in 1993, the International Color Consortium, they came up with ICC profiles, and what they actually did is they connected wavelengths with values to make them to work with these values in software, in computers, and and now we use these values in printers. So they invented color models we use to work with colors. And you all have heard of LAB and LCH and XYZ color modules. So this is what the International Color Consortium invented. I would say the most important, or the most common we know, is the LAB module, and this is how it looks like. The LAB module has 3 grades, an A, and B, and an L. The L goes from 0, which is black. That means no light, no reflection, no nothing. L100 is white. It's the widest white possible. So the light of the sun, the whitest light the human eye is able to see. Then we have the A that goes from -128, that is green, to 0, that is where it hits the LX, and to +127, this is red. And then the B goes from -128, this is blue, then again 0, that's where it hits the L, to +127, this is B. And so you have 3 coordinates, L, A, and B, and with these 3 coordinates you can address a special point within this module. So you can address a special LAB value, and this LAB value is connected to a wavelength. So this is an absolute color value. And due to these LAB values, we are able to communicate color and to use color in digital environments, like on computers and digital printers and stuff like that. Due to this LAB value, we have the delta E. This is another value, and delta E describes the differences between 2 colors. It means a delta E of 0 means there is no difference between 2 colors, so both colors are exact the same. The higher the delta E gets, means the bigger the difference between these colors. And where does delta E stands for? The E stands for Empfindung, and that's a German word, and that actually means perception. So it is delta perception. That is the idea behind delta E. There are different formulas for delta E. So the first one that came up was just delta E. Then in 1994, there was delta E 94, and in 2000, the delta E 2000. What changed? The delta E calculation is a mathematical formula you just use to describe the differences of 2 points within this LAB module. But this is a kind of a linear mathematic formula, but our eyes don't work linear, not at all. So for some colors, the human eye is much more sensitive than for others. For example, in yellow, it's hard for the eye to see differences, and in a red or green, even small differences are visible for the human eye. That means a linear mathematical formulation will not work. So with every update, they kind of tweaked the formula that it fits the human eye better and better. So all these formulas are not wrong. They're all still valid, but yeah, the delta E 2000 is the more accurate. Yeah. Then just to give you an idea what values might mean. So the highest acceptable delta E value is 5. This is by Color Alliance, or in Europe it's FOGRA. They said if a color difference is higher than 5, this is not acceptable, and then it's a different color, and this is not acceptable in a production printing. And the lower the LAB value, the more accepted it is. And as I said, the delta E of 0 means you are able to reproduce the color 100% correct, and that's what you actually need. This is also something I really need to tell you. It's that LAB or LCH, XYZ, so all these color modules, they are color. So they describe a color. They describe an absolute value. And unfortunately, a lot of the color communication still happens in RGB and CMYK values. But an RGB value or a CMYK value isn't a color. It's an amount of something. So what is cyan? What is 100% cyan? Yes, we have a rough idea what color to expect, but is it a bluish cyan? Is it a greenish cyan? What kind of cyan is it? So the information 100% cyan doesn't give us an absolute color value. And if you start mixing CMYK, then it's getting even worse. And in the digital printing industry we are in, it's also quite bad because there is no real standard. So in offset printing, for example, CMYK, so the pure colors, they are standardized and they are more or less the same. From every manufacturer you get it. In the digital printing industry, everybody does his own stuff. So if you get a sign from Durus, for example, it is a different sign from if you get it from EFI. So you have two printers, they maybe use the same printhead, you print the same material, you print just 100% sign, and you get 2 different colors. So CMYK, RGB are just amounts of something. Only LAB, LCH, whatever, so the color modules, that is an absolute color. This just shows it, for example, so you have a color on the left. This is an RGB value. This is, for example, a customer gives you. And on the 4 examples, you see you printed you kept the RGB values and you get different colors. And here you did it the other way around. You kept the LAB value, but that will cause totally different RGB values, but the color, so the LAB value, is exactly the same. So LAB is color. RGB CMYK is not. What describes the color? That are ICC profiles. You all heard of ICC profiles. An ICC profile is nothing special. It's actually, simply said, it's something like an Excel sheet where you have CMYK, or depending on, so here we have a CMYK profiles, so coded FOGRA or Greycall 2006 that are CMYK profiles. So they're kind of Excel sheets. They have all possible combination of CMYK. And next to it, you have the LAB value. So the ICC profile describes when you print whatever, 10% cyan, 10% magenta, 10% yellow, and 10% K, then you get this color. So then you connect the CMYK values of a printer, for example, with color. So that is important to know. How does color management work? So on the left side, you have your sources. So it's a camera or a file with RGB values. So this is what the detector, or on the camera, or in the file, it's so using, for example, an Adobe product to create a file or to create a color, and the ICC profile, so the input profile in this case, describe which CMYK values or which RGB values you used. And then in the color management, you see that the LAB values, they got transferred to the output device, so the screen or the printer, and then the color management system checked for these LAB values in the output profile, and it's okay to reproduce this LAB value on this printer, for example. I need these CMYK values, and if you see the CMYK values, for example, from the source and from the printer, they are totally different, but the color is the same because we reproduce the same LAB value. This is important. I will skip this because we run out of time, but this is important for you to know. This is just a comparison. So this is the comparison of an CMYK profile, so the color space of an CMYK device, that's the small yellow one, and an RGB device, that's the big white one. So this is the shape this color space would have in this LAB module. So this round module, this is the shape within this LAB module. And as you see, the RGB color space is 3 times bigger than the RGB color space is 3 times bigger than the CMYK profile. And this is something we need to deal with. So for example, if you look on the right picture, there are a lot of colors outside the color space of the CMYK color space. So, and if you say, okay, this is, for example, the white color space is a customer file, and there are colors, and the customer wants us to print these colors, then we are not able to print these colors. And this is where one part of the color management starts. That's where rendering intents come in place. I hope you all heard about it. So what is a rendering intent? And a rendering intent takes care that the colors that are outside the color space of your printer, for example, so outside this yellow color space, that they somehow get in there, because you need to print these information somehow. Even if you are not able to reproduce the color 100% exactly, something needs to happen with this color. So they need to come in your color space. And depending how big the difference is between the input, so the difference from the file and what your printer is able to print, the more the rendering intent needs to work. So we have four rendering intents, 4 important rendering intents. Maybe you heard it's perceptual, it's relative colorimetric, it's absolute colorimetric, and it's saturation. These are the 4 common, or actually the 4 rendering intents out there. There are some steps in between. So maybe you heard about relative colorimetric is black point compensation. I will tell you later what that means, but actually this is a relative colorimetric rendering intent. So what does a perceptual rendering intent? A perceptual rendering intent will move the colors, so 4, 5, 6, that are outside of our color management, of the color space of our printer, for example. We'll move them in there, and the dots 1, 2, 3. So actually colors he is able to reproduce, he will change them as well. So he will change all colors, and we'll kind of squeeze them. So I always explain it with a sponge. So you have a small glass and you have a sponge, and then you just squeeze the sponge to fit it in this glass. So you still have the entire sponge, so you didn't cut off something, but the difference is, so the holes in the sponge, they're just smaller, but the entire sponge is still there. The next but that means, and it's important for us to know, a perceptual rendering intent touches all colors. So even the color he is able to reproduce, he will change them. So this is not a color correct rendering intent because it will change all colors. When do you use it? For images, for example. If you have long black hairs you want to print with a lot of details and shadows and stuff like that. So a lot of dark information. And on a picture, it's not that important that the color is 100% correct. It's important that the picture looks nice, so that to keep the details, and when you use the rendering intent perceptual, the details in the hair will still be there, but the hair in general will be lighter. But on a picture, in most of the cases, that's not that important that the color fits, but it needs to look nice, as I said. The next rendering intent is colorimetric. What colorimetric will do, it will put the colors 4, 5, and 6 on the border and will not touch 1, 2, 3. That means the colors 4, 5, 6 will become one color because it's the same spot on the edge of our color space. So he will print these colors as good as possible, and it will not touch 1, 2, 3. So this is a color correct rendering intent. It will print the color he's able to reproduce. He will print them correctly, and the others as good as possible. If we would print this black hairs again, this will be just one black thing without any details, without any shadows, because all these different blacks will be merged to just one black, so that won't look nice. But if we print logo colors and just colorful images and the color counts, then colorimetric is the right rendering intent for us. The difference between relative and absolute colorimetric is that relative colorimetric doesn't touch the white. So the white point in the file and is automatically the white point of the printer. So even if the white in the file is different than the white of our media we print on, he just doesn't take it. So the white is relative. In colorimetric, an absolute colorimetric, he will take the white out of the source and will try to simulate the white. So this is only used for proofing environments and stuff. So in production, we never work with absolute colorimetric. This is only for proofing environments where the white, the media white, has an influence. The fourth one is saturation. And this is just if you want to print colorful. As you see, this is not color correct as well, because he will move 1, 2, 3 as well. So it will work from the colors that are outside. He will work as colorimetric. So we'll put everything on the edge, on the border, and tries to maximize the color of 1, 2, 3. So we'll move them more to the border as well to oversaturate them. So if you just need colorful prints and the color itself is not that important, then saturation might be a rendering intent that helps. So these are the color management basics. Then some steps about profiling. Profiling and the entire color management thing, this is something you can easily fill 2-3 days with such a presentation. So I have only 30 minutes, so I need to hurry. I just picked the, in my opinion, most important parts out of the profiling, and this is one part is the linearization, because in most of the cases, if something is wrong with colors at a printer, in most of the cases there's something wrong with the linearization. So what is the linearization? We want our printer to print linear. That means that if we say we want to have 50% cyan, for example, that we get 50% cyan on the media. So the right picture is that what we want, what we need, what is important. The left picture is the reality. So as you see, it is a curve. And so, for example, if you would give the information, we want 50% cyan, in this picture, we would get something like, I don't know, 70, 80% cyan. So it would be impossible for us to color manage, because we expect 50 and we get 80, and or we expect 60 and we get 90. So this is uncontrolled. So we need to linearize our printer. It's an easy step. It's just printing a chart with steps. So for example, sine from 0 to 100% in 5% steps. The measurement device reads it, and then he creates the correction curve. That is the picture in the middle. And as a result, we get the right picture, so the linear printing. This is something. This is so far so easy. So this is easy. There's nothing special. The problem starts. What makes a printer nonlinear? So this is something. This is constantly changing. So if the temperature in the print environment changes, if the humidity changes, if you get a new ink batch, if you get a new media batch, that all has an impact on how linear your printer prints. So this is constantly changing. So this is something we really need to control, and this is something also special in the large format printing industry. If you go to a offset print shop, for example, the first thing the operator does in the morning when he starts his machine, he does a linearization. That's the first thing. And even during printing, every 100 pages, 200 pages, he takes a sheet out there and does a linearization. So even during the printing process, they're constantly linearizing their device. And if you talk to a digital printer, yeah, sometimes they do it once a month. Most of them never did it. And this is where the problem starts. It's not a difficult thing. It's just a few lines you need to read, and then your print is linear again. But this is the foundation actually of color management, because when your linearization is off, then you are in an uncontrolled divide, and you have the best color management afterwards, but it's uncontrolled, so it can do nothing. And now to a special thing. This happens in all print technologies, but it's very strong and really very bad in dye sublimation on fabrics. So the picture on the left is the result of a linearization reading. So this is the curve I get on a dye sub printer from the linearization. So this is the actual status of this printer. And on the right, we see the U. So this is the view of the curves within this LAB module. So we'll look from above is the LX, and the horizontal line is the A, and the vertical line is the BX. So this is our readings. And in the sine, we see something strange. It goes back. So the first measurements from the middle, it goes out, it goes to the maximum, and then it turns. And even the magenta turns a little, not that bad as the sine, but it turns. This is what we call a U shift. And what's happening is the color changes, and we lose color. So we add ink. Yeah, so this is the first patch is 5% ink, 5%, and then 10, blah, 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 and you see the first couple of percentages it moves outside, and then it turns back. What I showed you on the left are chroma values. Chroma is also a value out of this LAB module, and it describes the amount of color. So the higher the chroma value, the more color you have. So the more colorful you are. Chroma doesn't describe a color. So it's not that a chroma of 50 is red or something. No, a chroma of 50 can be every color. It's just something like how far from the middle. So from the L-ax you are away. So the far away, the more colorful you are. And on the left, you see that the maximum chroma you have at an ink level of 40%. And when you go higher with your ink density, your chroma goes down. So that means you add more ink on your surface, but you lose color. And this is something visually you don't see that. This is something you only see when you use a measurement device, or this is only shown by a measurement device. The human eye is not able to see that, because what's happening is the color is getting darker. So, and that's the reason it looks, yeah, more colorful to our eyes, because it's getting darker. But actually we lose color. So we go back to the middle, so back to the gray X. And this is something you really need to take care of in color management. So when you do the ink limiting in profiling on dye sub, because what's happening there, first of all, you lose color. And now you say, okay, I would limit this as at 80% sign. So you did not cut off the 40%. So the color is still there. That is right. But the color management algorithm that calculates the ICC profile, it's very difficult for them, because the color management algorithm that calculates the ICC profile, that says the more ink I add on the media, the more color I get. And here it's total difference. So it's really hard to calculate it. So you get really shitty profiles, and you put too much ink on your media. So you don't need this ink. So you can save a lot of ink. And that does not mean that you save money. That also gives you a lot of other solves a lot of other problems, because you have less ink on the media. So, and you print bigger color spaces, and so there are only benefits. And you can only use this chroma method when you use a color management device and when your software is able to show you the chroma values. Some of them are, not all, and if your RIP software is not able to show chroma values, there is other software to measure or to view chroma values. So this is an important thing in dye sublimation. So you save ink and you get actually bigger color spaces. Another important thing or another thing that happens in dye sublimation is the media surface. So when you see on the left, you see a textile, and I just cut it in half. And when it's laying next to each other in the same direction, it is a white textile. When you turn it at 45 degrees, you already see what's happening. So I only turned it. It's still the same fabric. I only turned it. And it looks like it's a totally different color. Same with 90 degrees. And then I put both on 90 degrees, and then they're all the same again. And this is just the white media without any ink on there. So just imagine when you print ink on there. So if you in production, if you nest different jobs and you in different directions, so you turn in the job at 90 degrees to save ink, then this might completely destroy your color, because yeah, you see what's happening. Just turn the media at 90 degrees, it will give you a totally different color. So this is also a very important thing. This happens with all medias, with all surfaces, so even with vinyls and banner, but as the surface is much smoother, it's not that visual, so you really see it really bad on the rough structure of a fabric. Yeah. Next thing, measurement devices, also important. So this is just an overview of some measurement devices we have out there. And the important thing, and where it goes wrong most of the times, are the illumination conditions. So the light conditions we use within our measurement device. So these are settings you can use in a modern measurement device. M0, M1, M2, M3. Maybe you heard of it. I will just explain what it means. M0 is a standard which is no standard. So this is before they defined the standard, everybody could put a lamp in their measurement device as they want, and there was nothing regulated or so. And to not lose these devices, they came up with the standard M0. That means you can do whatever you want. So M0 means it's not defined. The first real standard is M1. And what they did, they said, okay, we put a light source that needs to give 5,000 Kelvin. So D50 means it's 5,000 Kelvin. And they defined the UV amount the lamp needs to respond on. Then M2 is the same light source, so it's D50, but what they do is they cut off the lower part. So they start measuring at 420 nanometers. They do this to illuminate optical brightness. So you have optical brightness on most of the medias out there, and for sure a lot of optical brightness on fabrics. And these optical brightness, they trick our eye. So they make the media appear whiter than it actually is. Unfortunately, they don't trick measurement devices. So measurement devices see the real color. They react different on the optical brightener. And to cut the influence of optical brightness out, that you just cut off the UV part of the measurement, and then you're actually good. M3 is a polarization filter. This is not that often used in our industries. In some case, for UV printing, for special application. This is for reflective surfaces and stuff like that. So when you want to measure wet inks or wet surfaces and stuff. So there are some special applications where M3 makes sense, but actually it is, in our industry, it's M1 and M2, and old measurement devices use M0. Just to show you what's happened, on the upper right, you see 3 measurements of the exact same media, just used different measurement conditions. So as you see, the LAB value of the white you get is, so the L is 94 on all measurements. So the LX, there's no big difference. On the AX, there is a little difference, but it's really bad on the B. And the minus B is the bluish. So the B goes, the negative part of the BX is the blue. So that means the M0 measurement has a B of -9, and the M1 has a B of -12. Why is that? Because we have a higher light temperature. So when we go back, we see the light source of the M0 is something like 2800 Kelvin. So when we remember the picture in the beginning, this is a very reddish light. D50, so 5000 Kelvin is a very neutral light source. And that's the reason it gives us a more accurate measurement. And when we use M2, we see most of the part is happening in the bluish part. So we got from -12, we moved to -4, because we cut off the UV part of the measurement. And again, we only talk about the naked media, so just the pure white of the material without any inks on it. So you can imagine how big the differences are on printed surfaces just if you change the measurement conditions. So it's really important to have the right measurement conditions, and yeah, I recommend to use M1. So all the new measurement devices, they support M1, and that's what you needed. That is, according to the ISO standard, M1 is the correct measurement condition. This is just an image that shows the same picture in the same room, just with different light sources. So just to get an idea. Going back to fabric measurements, so to the textile, the aperture of a measurement is also quite important. There are devices out there that support 2, 6, and 8 millimeters measurement aperture. So for example, the old, the I1, the X-Rite I1, the old devices, they support 2 millimeters. The new device, the I1 Pro 3, is available in 2 and 8 millimeter. So there's the I1 Pro 3 Plus, that's the 8 millimeter version, and the normal one is the 2 millimeter version. The Barberi Spectral LFP device, they support 2, 6, and 8. Then there is the SpectroPad, that's a hand device from Barberi that supports 6 millimeter. So depending on your application and the media you use, so for sure if you print on fabrics, the bigger the aperture, the better. And this example shows why. So when you just have a small 2 millimeter aperture, it might happen on a fabric just to just print a hole, so an error without any color on it. So the bigger the aperture, the bigger the chance, or the more color information you get, and the more accurate your ICC profile is. And actually, you can also use this for if you have a printer with a very low resolution, it's the same. So you just, if you have a big aperture, you just measure more dots, more printed dots than with just a small 2 millimeter aperture. So this is important thing in dye sublimation textile printing to have a measurement device with a big aperture. So it's a Barberi Order i1 Pro 3 Plus. That's it for now. Are there any questions, Kylie? Hello?
No, I don't see any questions right now. Does anybody have any questions for Andre? I know we covered a lot of information today. Well, Andre and I will hang on for a couple minutes. If anybody wants to type a question or unmute themselves and ask, we'll be here.
Yes. Otherwise, send an email to your Ultraflex contact and they will just forward it to me. So I'm happy to help or to answer questions. But I thought I hope this was a good overview about color management and why important it is and why it helps you to solve issues.
Yeah, over the years, I've traveled a lot with Andre and doing some profiling of our Vortex fabrics, and it definitely makes a really large difference having the proper equipment in the proper settings. So it's definitely something I think you should invest in and learn about. So hopefully when things open back up, you'll be able to have some great consistent outputs on various pieces of equipment.
Yes.
Yeah, so if nobody has any questions, Andre, thank you so much for joining us today, and I hope everybody has a great week. Bye, everyone. Thank you.
Okay, bye, everybody.